By mid-2024, China's Chang'e-6 mission quietly accomplished something that stunned the global space community. While NASA was still testing rockets and SpaceX was launching satellites, China had successfully returned the first samples ever collected from the lunar far side. The mission's findings, reported in April 2025, revealed unexpected water content differences in the far side's mantle that challenged existing theories about lunar formation. The numbers from 2025 reveal a shocking truth about who's really winning the space race, and it's not who you think. What did Chang'e discover in those far side samples that has every major space agency scrambling to catch up? The answer lies in data that goes far beyond simple mission success rates. The numbers that changed everything. China's space program funding has grown substantially over the past 5 years, reflecting a strategic commitment that sets it apart from traditional space powers. This investment pattern reveals something more significant than simple budget increases. While NASA's Artemis program has consumed massive resources since 2019, with the first crewed lunar landing now pushed beyond 2025, China has executed multiple successful lunar missions, including the historic far-side sample return, at considerably lower estimated costs than NASA's heavy development budgets. The mission's success rates that emerged from recent reporting tell a compelling story. China's Chang'e program maintains perfect execution across all lunar missions, from the early orbiters to the complex sample return operations. NASA's recent track record shows a different pattern, with the uncrewed Artemis 1 mission experiencing multiple delays and the Space Launch System rocket facing ongoing technical setbacks. The European Space Agency's lunar ambitions remain largely theoretical, while Russia's Luna program struggles with funding constraints and technological hurdles. India's Chang'e missions show promise but operate on a much smaller scale with limited frequency. The timeline acceleration reveals dramatic disparities in operational tempo. China launched Chang'e-6 in 2024, executed a successful far-side sample return, and immediately began preparations for Chang'e-7 and 8 missions scheduled for the coming years. This represents a mission cadence that no other nation can match. The contrast becomes more pronounced when examining the complexity of China's operations versus the delays affecting other space programs. Manufacturing efficiency data shows China producing spacecraft components at significantly lower costs than American equivalents while maintaining comparable quality standards. Chinese space manufacturers delivered the Chang'e-6 orbiter, lander, and sample return capsule as an integrated system that demonstrates remarkable cost-effectiveness. This efficiency extends beyond individual missions to encompass entire program architectures. The personnel deployment statistics paint an equally revealing picture. China's space workforce has expanded substantially, with a significant portion focused specifically on lunar operations. These workers operate across major facilities dedicated to lunar mission development, testing, and control. The concentrated approach creates fundamental differences in operational efficiency and decision-making speed compared to more distributed models used by other space agencies. Launch frequency represents another area where China's systematic approach yields superior results. The Long March 5 rocket, China's heavy-lift vehicle for lunar missions, achieved multiple successful launches compared to limited Space Launch System operations. This ratio reflects not just manufacturing capacity, but also operational readiness and mission planning sophistication. Testing methodologies reveal deeper philosophical differences between space programs. China conducts extensive ground-based testing for every mission component, often spending extensive time in simulation before hardware reaches the launch pad. This methodical approach contrasts with other agencies' tendencies to identify and resolve issues during flight testing. The Chinese approach prioritizes mission success over speed to market, resulting in fewer setbacks but more thorough preparation cycles. International collaboration patterns show China establishing partnerships with multiple nations for lunar research and development. These partnerships operate under bilateral agreements that give China significant control over technology sharing and mission planning. Other space programs include more signatory nations, but many provide limited tangible contributions beyond political support. The quality versus quantity dynamic favors China's approach, with partner nations contributing actual hardware and expertise rather than symbolic endorsements. Resource allocation efficiency becomes apparent when examining how each program distributes funding. China dedicates the majority of its lunar budget to hardware development and mission operations, with smaller portions allocated to research and administration. Other space agencies show different spending patterns with higher administrative overhead and contractor management costs. This allocation difference explains how China accomplishes more with focused resource deployment. The geographic distribution of capabilities tells another story about program structure. China concentrates lunar operations at primary locations including the Wenchang Space Launch Site, the Beijing Aerospace Control Center, and the Xi'an Satellite Control Center. This concentration enables rapid communication and coordinated decision-making. Other space programs operate across multiple centers and contractor facilities, creating communication delays and coordination challenges that impact mission timelines. Supply chain analysis shows China controlling the vast majority of its lunar mission components through domestic manufacturing, compared to much lower domestic content for other space programs. This vertical integration gives China greater control over quality, costs, and delivery schedules while reducing dependency on international suppliers. The strategic advantage becomes clear when geopolitical tensions affect technology transfer and component availability. Innovation speed measurements track how quickly each program incorporates new technologies into operational systems. China's lunar program has rapidly adopted advanced ion propulsion, autonomous navigation, and sample processing technologies within short time frames of laboratory demonstration. Other space agencies show much longer technology adoption timelines from laboratory proof of concept to operational deployment. This acceleration gap allows China to maintain technological leadership in rapidly evolving fields. The systematic Chinese advantage across multiple dimensions of space operations represents something far more significant than simple efficiency gains. These patterns reveal a fundamental transformation in how lunar exploration operates, moving from the government-led, prestige-focused model of earlier eras to a resource-oriented, commercially driven approach that prioritizes sustainable operations over symbolic achievements. This shift in methodology becomes most apparent when examining where China has chosen to focus its most ambitious operations. While other nations concentrate on familiar territories, China has systematically developed capabilities in the most challenging and strategically valuable lunar real estate. The far-side advantage expands. Chang'e-4's landing in Von Karman crater 6 years ago marked the beginning of China's transformation of the lunar far side from unexplored territory into an operational advantage. The U-22 rover continues its multi-year operations, making it the longest operating lunar rover in history as it traverses terrain that remains invisible to Earth-based telescopes. While other nations focus their lunar ambitions on the familiar near side, China has established the foundation for permanent far-side capabilities. The strategic implications of this positioning become clearer with each passing month as China's far-side operations expand beyond simple exploration. The choice to establish far-side operations required solving communication challenges that had deterred previous missions. China deployed the Chang'e relay satellite at the Earth-Moon L2 Lagrange point, creating a constant communication bridge between Earth and the lunar far side. This satellite maintains continuous line of sight to both locations, enabling real-time control of surface operations and data transmission. The positioning at L2 offers gravitational stability that requires minimal fuel for station keeping, allowing Chang'e to operate for years without significant orbital adjustments. This communication infrastructure represents a technological achievement that gives China control over far-side communications access. The relay satellite system has evolved beyond basic communication into a sophisticated network supporting multiple simultaneous operations. Chang'e-2, launched in 2024, provides enhanced bandwidth and redundancy for the expanding far-side mission portfolio. The dual satellite configuration enables continuous coverage even during maintenance periods and supports high-definition video transmission from the lunar surface. This communication capability allows Chinese mission controllers to operate far-side equipment with the same precision as near-side missions, eliminating the operational disadvantages that previously made far-side exploration impractical. Radio astronomy opportunities on the far side offer China unique advantages unavailable anywhere else in the solar system. The lunar far side remains shielded from Earth's radio emissions, creating the quietest radio environment within millions of kilometers. This natural radio silence enables detection of cosmic signals that would be possible to observe from Earth or near-side locations. Chang'e-4 deployed China's first far-side observatory, including a low-frequency radio telescope capable of detecting signals from the universe's earliest epochs. The scientific data collected from this radio-quiet environment provides insights into cosmic microwave background radiation and the formation of the first stars and galaxies. Geological composition studies reveal that far-side terrain differs fundamentally from near-side materials, offering China access to lunar resources with unique characteristics. The South Pole-Aitken Basin, where Chang'e-4 operates, exposes mantle material rarely found on the lunar surface. This ancient impact structure provides access to minerals and rock formations that formed during the Moon's earliest geological periods. The compositional differences suggest the far side contains resources that could prove crucial for future lunar operations, though the full extent of these differences became clearer through sample analysis techniques. China's far side operations have expanded to include monitoring stations that track celestial phenomena invisible from Earth. The absence of atmospheric interference in Earth's electromagnetic noise allows for astronomical observations of unprecedented clarity. Chinese instruments on the far side have detected cosmic ray patterns and gravitational signatures that Earth-based observatories cannot measure. This positioning provides China with capabilities for monitoring solar storms and space weather events that could affect satellite operations and power grids on Earth. The strategic value of this monitoring capability extends beyond scientific research into practical applications. Mining exploration on the far side has revealed mineral deposits that appear more accessible than equivalent resources on the near side. The unique geological history of the far side created concentrations in different patterns compared to the near side's Maria formations. Chinese rovers have identified titanium-rich deposits within reach of surface operations, along with rare earth elements that could support lunar manufacturing operations. The far side's lower gravity and lack of atmospheric interference create conditions for processing and launching materials to Earth orbit or deeper space destinations. Solar power generation on the far side offers advantages that solve critical energy supply challenges for lunar operations. The far side experiences the same day-night cycle as the near side, but its isolated location eliminates electromagnetic interference that can affect power grid operations. Chinese solar arrays on the far side operate at higher efficiency rates due to the lack of radio frequency interference from Earth. The positioning also enables power transmission experiments using microwave beaming technology that could eventually supply energy to Earth-based receivers. These power generation capabilities support extended surface operations without dependence on nuclear power sources. China's far side infrastructure has grown to support multiple simultaneous missions operating across different regions of the hemisphere. The communication relay network enables coordinated operations between rovers, landers, and orbital assets without requiring direct Earth contact. This operational independence allows China to conduct complex multi-phase missions that would be impossible for other nations without similar relay infrastructure. The far side base serves as a staging area for missions to the lunar South Pole and provides logistical support for deep space operations targeting asteroids and Mars. Ground-penetrating radar has mapped subsurface structures and geological formations that could shelter future operations. The far side's unique position relative to Earth's magnetic field enables studies of solar-wind interactions and space weathering processes that affect all airless bodies in the solar system. Seismic monitoring equipment has detected moonquakes and subsurface activity patterns that differ from near-side geological processes. China's commitment to far-side operations represents a calculated strategy that prioritizes long-term advantages over short-term achievements. While other nations pursue symbolic milestones, China has built the foundation for permanent lunar operations in the most strategically valuable location available. The far side provides opportunities, resource access, and strategic positioning that cannot be replicated elsewhere, giving China sustainable competitive advantages that will persist for decades as lunar operations expand. The true value of China's far-side positioning became fully apparent when the first samples from this hidden hemisphere returned to Earth, carrying secrets that would reshape scientific understanding of lunar formation and resource potential. Sample returns that stunned scientists. When Chang'e-6 returned to Earth in June 2024 carrying 1.935 kilograms of lunar material, the scientific community expected valuable data from the first far-side sample return mission. What they discovered in those samples defied expectations and raised questions that have other space agencies reconsidering their entire approach to lunar exploration. The material collected from the South Pole-aitken Basin contained geological formations unlike anything seen in the Apollo samples or the previous Chang'e-6 side collection. Within weeks of analysis, it became clear that China had brought back evidence of processes that fundamentally challenge existing theories about lunar formation and evolution. The basaltic rocks retrieved from the far side tell a story spanning 2.8 to 4.2 billion years of lunar history. These volcanic specimens preserve records of ancient lunar activity that occurred when the moon's surface was dramatically different from today's barren landscape. The age dating reveals multiple periods of volcanic activity extending far longer than previously documented, suggesting the lunar interior remained active much longer than models predicted. This extended volcanic timeline indicates the moon possessed greater internal heat sources and more complex geological processes than scientists understood from near-side samples alone. Laboratory analysis revealed the most startling discovery within the first month of sample processing. The mantle material beneath the far side contains significantly less water than equivalent regions on the near side, creating an asymmetric distribution that supports the giant impact hypothesis of lunar formation. This water content difference suggests the moon formed from debris created when a Mars-sized object collided with early Earth, with the impact energy and subsequent cooling creating distinct hemispheric characteristics. The finding provides direct physical evidence for theories that had remained largely theoretical due to lack of far-side samples. Chinese laboratories identified KREP material within the far-side samples, a substance rich in potassium, rare earth elements, and phosphorus that forms between the lunar crust and mantle. The presence of KREP in far-side samples confirms that the magma ocean that once covered the moon cooled through similar processes on both hemispheres, despite their current geological differences. This discovery indicates that the moon's early formation involved planet-wide molten conditions that gradually differentiated into the current crustal structure. The KREP layer represents a crucial boundary zone that contains concentrated rare elements essential for understanding lunar geochemistry. The analytical techniques employed by Chinese scientists have advanced beyond capabilities available to previous sample return missions. Electron microprobe analysis, X-ray diffraction, and mass spectrometry systems operating at the Chinese Academy of Sciences can detect trace elements and isotopic signatures at parts per billion levels. These instruments can identify mineral phases and chemical compositions that would have been invisible to 1970s technology used on Apollo samples. The enhanced analytical precision reveals microscale features and chemical gradients that provide detailed information about formation temperatures, cooling rates, and subsequent alteration processes. Mineral compositions found in the far side samples show distinct differences from near side materials that have profound implications for resource extraction planning. The titanium content in far side basalts exceeds near side concentrations by factors of 3 to 4, creating ore-grade deposits that could support industrial operations. Rare earth element concentration shows similar enrichment patterns, with some samples containing neodymium, europium, and yttrium at levels that would be considered economically viable on Earth. These elevated concentrations suggest the far side experienced different cooling and differentiation processes that concentrated valuable elements. The sample processing revealed unexpected organic compounds that formed through interactions between solar wind particles and lunar minerals over billions of years. These compounds, while not indicating biological activity, demonstrate complex chemical processes occurring on the lunar surface that could be harvested for future operations. The organic molecules include carbon-hydrogen chains that could serve as feedstock for producing plastics, fuels, and other materials needed for lunar settlements. The discovery suggests the lunar surface acts as a chemical reactor, continuously producing useful compounds through space weathering processes. Chinese researchers discovered evidence of subsurface ice deposits within the crystalline structure of far-side samples that were previously undetected by remote sensing instruments. The ice appears as microscopic inclusions within mineral grains, preserved from ancient comet impacts that occurred billions of years ago. This subsurface ice represents a water source that remains stable against sublimation and could provide resources for future lunar operations. The discovery method using sample analysis suggests similar ice deposits may exist throughout the lunar interior, accessible through mining operations. Analysis revealed isotopic signatures that indicate the far side experienced different bombardment patterns during the late heavy bombardment period 4 billion years ago. The isotope ratios of platinum group elements showed distinct patterns compared to near-side samples, suggesting the impactors that shaped the far side came from different regions of the solar system. This bombardment history affected the distribution of volatile elements and created the unique geological characteristics that distinguish far-side terrain from near-side Maria formations. The samples contain microscopic glass spherules formed during ancient impact events that preserve records of the lunar magnetic field from billions of years ago. These glass beads contain iron particles aligned according to magnetic field directions that existed when the impacts occurred. The magnetic signatures indicate the Moon possessed a much stronger magnetic field in its early history, generated by a liquid iron core that has since cooled and solidified. This magnetic field evidence helps explain how the Moon retained its early atmosphere and water content longer than previously thought possible. Chinese laboratories identified previously unknown mineral phases that formed under the extreme pressure and temperature conditions of the South Pole-Aitken impact event. These minerals, including high-pressure polymorphs of common silicate minerals, provide direct evidence of the energy involved in creating the solar system's largest impact structure. The mineral assemblages indicate impact pressures exceeding 60 gigapascals and temperatures above 2,000 degrees Celsius, conditions that created unique materials not found elsewhere in the solar system. The commercial implications of these discoveries extend beyond scientific curiosity into practical applications for lunar industrialization. The concentrated rare earth elements could support manufacturing operations for electronics and advanced materials needed for space infrastructure. The titanium-rich deposits provide raw materials for structural components and spacecraft manufacturing. The organic compounds offer feedstock for chemical processing operations that could produce everything from rocket fuel to life support consumables. However, the most significant aspect of these discoveries may be what China has chosen not to publish in international scientific journals. The 2-year delay between sample return and partial data release suggests extensive classified analysis of materials with strategic importance. Independent scientists note that published results focus on basic geological processes while avoiding detailed discussion of resource concentrations and extraction methodologies. This selective disclosure pattern indicates China has identified commercially valuable materials that warrant protection from international competitors. Among the most intriguing discoveries was the identification of Chang'eite, a new mineral containing helium-3 that China first discovered in Chang'e-5 samples in 2020. The Chang'e-6 far side samples revealed this mineral exists in higher concentrations across the lunar far side, building on China's systematic mapping of helium-3 distribution that began with Chang'e-1 in 2007. Chinese scientists have conducted extensive experiments on optimal methods for heating lunar regolith to release helium-3, emphasizing the potential for future fusion energy applications. While helium-3 fusion remains decades away from practical implementation, China's comprehensive mapping and extraction research positions them uniquely to exploit this resource when technology advances make it viable. The Chang'e-6 samples have fundamentally altered scientific understanding of lunar formation while revealing resource concentrations that can determine who controls future lunar economic development. The far side materials contain the keys to understanding how rocky planets form and evolve, while simultaneously providing the raw materials needed to establish permanent human presence beyond Earth. These discoveries position China as the gatekeeper of both lunar science and lunar commerce, with exclusive access to materials that may prove essential for humanity's expansion into the solar system. Yet, among all the valuable resources identified in these samples, one element, the helium-3 gold rush, begins. Helium-3 represents the ultimate prize in lunar resource extraction, containing energy potential that could revolutionize global power generation. A single gram of this rare isotope contains enough energy to power an average home for over 3 years, yet Earth's entire supply amounts to barely 15 tons trapped in natural gas deposits. The lunar surface contains an estimated 1.2 million tons of helium-3, deposited over billions of years by solar wind particles embedding themselves in the regolith. While fusion reactors using helium-3 remain largely theoretical for most nations, China has made significant advances in fusion technology development, building on decades of research that began with their systematic mapping of helium-3 distribution, starting with Chang'e-1 in 2007. Global energy demand continues rising while fossil fuel reserves diminish and renewable sources struggle to meet baseline power requirements. Coal plants still generate substantial electricity in developing nations, while nuclear fission creates long-term waste storage problems that have plagued the industry for decades. Helium-3 fusion produces no radioactive waste, generates no greenhouse gases, and offers energy density thousands of times greater than chemical fuels.